Hello everyone, this is going to be the last video before your midterm. I don't think I can get to chapter 18. I'm sorry, but I hope there isn't too much on that during your midterm tomorrow. But this is going to be chapter 17. We're going to be dealing with aldehydes and ketones. This is actually my favorite chapter in the book, or it's one of my favorite chapters. I really like carbonyls and I enjoy their chemistry. So let's get into it. So the chapter is dealing with aldehydes and ketones, right? Chapter 17. And when we talk about aldehydes and ketones, we first have to know what they look like, right? So these are a classification of a group called carbonyls. So carbonyls have a C double bonded to an O, right? And then this C can be bonded to multiple groups, which makes them a different type of carbonyl compound, right? So with aldehydes, the carbon is double bonded with an oxygen, but it also has a hydrogen here, right, instead of a carbon. But with a ketone, it really depends. You can have multiple carbon bonds here as well as carbon bonds here. You can have like a phenyl group here. You can have anything. So the only difference is that in an aldehyde, this C is directly bonded to an H, but in a ketone, the C can be bonded to multiple C chains, right? Carbon chains, right? So they have similar chemistry, but if you think about it, the aldehyde is going to be a bit more reactive because of this hydrogen that is not taking any electron density away, right? So we'll get into that. So yeah, just make sure you know how to draw a ketone and an aldehyde. It's going to be very important. We're going to be dealing with a lot of these today, right? So some chemistry between them. So here I've drawn this ketone right here. I just have two methyl groups on the side. We know it's a ketone because none of these attached to the carbons are hydrogens, right? So this is a ketone. So let's take a look at the special chemistry that's with ketones and aldehydes in general. So if you look at this bond here, the C double O bond, it's not evenly shared, right? We usually think of covalent bonds, and the definition of a covalent bond is the sharing of electrons, right? But the thing is, these electrons are not evenly shared between this carbon and this oxygen, right? If you look at the periodic table, oxygen is actually going to be a bit more electronegative than that carbon, which means it's going to take these two double bonds and it's going to pull on them a little bit more than it does pull to the carbon. So that means we have a delta negative on the oxygen and we have a delta positive on the carbon. And in terms of chemistry and organic chemistry, this means this oxygen can act as a nucleophile, right? It can attack something, and something can attack this carbon, right? So we'll get into more of what that looks like right now. But first, knowing about aldehydes and ketones, we have to know how to make them, right? So making aldehydes and ketones, you're usually going to make them through, two different ways of making them right now. First off, you have oxidation, right? If you remember, this is from 40A. You have a primary alcohol, right? Something that looks like this, where it's just bonded to a bunch of hydrogens, this primary alcohol. And if you use an oxidation reagent like Jones or PCC, you can make an aldehyde, right? So you would use PCC because Jones is a little stronger. So if you use a primary alcohol and you react it with PCC, you're going to get an aldehyde. And then if you use a secondary alcohol and react it with either one, you're going to get a ketone, right? So you don't need to know the mechanism for these, but just try to form that memory bank and look up on these if you have trouble remembering. And then Friedel-Crafts acetylation. We just went over it. I'm missing the benzene ring here. Oops. We just went over it on our last chapter about electrophilic aromatic substitution. We have a benzene ring, and then if we react it with this carbonyl species with a halogen here, and react it with a metal and 3 of those halogens, we can substitute it onto this benzene ring, right? So these are the main two ways that you're going to make aldehydes and ketones. So we're going to go more into um, like their chemistry and carbonyl chemistry. And then again, another refresher on reducing agents. So this is important for synthesis. So let's say you're given an aldehyde and then the product is a primary alcohol, right? You may not know how to do that, but because we have oxidation reagents where we make a primary alcohol turn into an aldehyde, we can turn an aldehyde into a primary alcohol by the opposite of oxidation, which is reduction. So we have reducing agents, right? LiAlOH4, lithium aluminum hydride, and then we have NaBH4, which is a little bit less reactive and less strong, which is sodium borohydride. So it turns aldehydes, lithium aluminum hydride, turns aldehydes into primary alcohols, turns ketones into secondary alcohols, and carboxylic acids, if you remember from up here, it turns that into a primary alcohol. And then for sodium borohydride, aldehydes are turned into primary, and then ketones are turned into secondary, right? These are just um, some of the reagents that you would have to know. Okay, so let's go into a sample reaction of what you'll see. So here we have a ketone, right? This is these are methyl groups on the side of that carbon. And then we just have a regular nucleophile here with a negative charge. And like I said before, there is a delta negative on this oxygen. And then this carbon that's connected to that oxygen has a delta positive. And we have a very strong nucleophile since it's a negative charge, right? So it's going to attack this carbon right here. But if it attacks that carbon, it's going to attach to that carbon, right? And if it attaches to that carbon, I'm just going to draw it right here. C double bonded O, you can see how it has 1, 2, 3, 4, 5, 5 bonds. And from Lewis' theory, that can't happen. So what's going to happen is this double bond is going to go to the oxygen. The double bond, one of the shared lone pairs is going to go up to the oxygen. And if it goes up to that oxygen, it's going to make this species right here where this carbon is now fine, right? It has 4 bonds. It's completed its octet. But now this oxygen up here has a negative charge, which is what I denoted here with this negative charge, right? And then you can see how the nucleophile is still attached to this carbon right here, right? So we're just doing a simple reaction. It's sort of like an SN2 reaction. And then this is called a tetrahedral intermediate. If you look, this is sp2 hybridized, right? This carbon right here is sp2 hybridized. But now if you look at here, this carbon is now sp3 hybridized. And if a carbon or if a molecule is sp3 hybridized, most of the times it's in a tetrahedral formation. So which is why it's called a tetrahedral intermediate, right? And now we have our negatively charged oxygen, right? And if you react it with an acid, any acid, this is called an acidic workup. So here I just have the H3O acid. This can actually take the acidic H and then make this species where we have now uh, an alcohol here, right? So that's just a sample reaction. So what happened was the nucleophile attacked the carbon that's holding the double bonded O because this bond is not evenly shared. The bond goes up to the oxygen, and now I have a lone pair on the oxygen. And then if you treat it with an acid, it will go down to this formation of an alcohol. But if you actually look here, there is another thing that can happen if we don't react it with an acid, right? If we don't react it with an acid, the lone pairs from the oxygen can actually come down here and kick this nucleophile out again, making it the backwards reaction right here, right? So there is a reversible way of doing this, right? So reversible just means that it's in an equilibrium. It can either go to this side or it can go back to here, right? And What matters is how good this nucleophile is at being a leaving group, right? Because this double bond can form again between this carbon because it has lone pairs, right? And then this nucleophile can go out again and become a good leaving group, right? So this reversibility just depends on how good of a leaving group this nucleophile is. So if we have a bad leaving group, this reaction is not going to swing. This reaction is going to swing towards um, this side, right? Because it's not a good leaving group. So that means only a small percentage of it will come out to this formation, which is why we have it smaller. But in this case, since we do have a generic nucleophile, we do have to keep this in uh, equal, okay? So, and then another refresher is are called Grignard reagents. So Grignard reagents are a way of adding more carbon bonds to a molecule. And if you remember, oops, we have this species right here, where it's a carbon attached to an MgBr, right? So let's go back to this carbon has three hydrogens on it, right? So let's go back to Chem 6a about ionic bonds, right? What's the charge of magnesium? If you look at the periodic table, magnesium is an alkali metal. So that means it has a +2 charge, right? So it has a +2 charge. And what about bromine? Well, we know bromine is a halogen, so it has a -1 charge, right? In total, this makes up +1, right? And we know that we want to maximize the charge. So we want to make this neutral. And the only way to make this compound neutral is if we have a negative on the carbon, right? So this is actually a very interesting way of making carbon negatively charged. If we react it with this MgBr group, this carbon is now negatively charged. So instead of it looking like this, it sort of looks like this compound right here. See, it has a H, 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 and then it has a lone pair here with a negative, and then MgBr, which is a net +1, right? And then if they combine, like in here, it makes it a neutral compound. So because we have a good nucleophile in our carbon, the carbon can just attack this aldehyde, right, from the bottom because of this delta positive and this delta negative. And then the bonds are going to go up to that oxygen. And when we do that, we get this, right? The carbon just attached onto that carbon. And then this is called our tetrahedral intermediate. And let's think for a minute. Is it possible for this to come here and this leaving group to leave? It is. But is carbon a good leaving group? It's not a good leaving group. So the arrow is very, very tiny compared to this product, right? So because of that, we can treat it with uh, an acid, right? And then this oxygen will actually grab the acid again, and then we will form a alcohol here, right? So the reason why there's no reversible arrow of it going this other way is because if this carbon leaves as a leaving group, it can just react back again, right? Because it's such a strong base. And if you remember for 40A, weak bases make really good leaving groups, right? So carbon is a very strong base, which means it's not a good leaving group, okay? So let's talk about pH conditions when we're dealing with aldehydes and ketones. Right here, this is what we would call a basic condition, right? You see this OH is negatively charged, and we also have water as our solvent, right? So this OH is going to be like this with a negative charge here. And if you remember, because we have this delta positive on this carbon, we can react it with that carbon, and then this will go up, making this intermediate, this tetrahedral intermediate, OH plus H2O, right? and then this will have a negative. And then a couple things can happen here. Um, let's say this the lone pair comes back and then kicks out that hydroxyl. Is OH a good leaving group? OH is not a good leaving group, so the arrow here will be very, very tiny. It's going to be favored towards this reaction rather than the other direction, right? And then now we have a water here, and we have a that O is negatively charged. So we can grab that hydrogen, and then we go up to this compound, and then we're still with an OH, right? And then as you can see, the OH doesn't change, right? So this is what we would call a catalyst, right? This is a basic condition catalyst. So in basic conditions, this hydroxyl with the negative O will attack this carbon on the double bonded to the oxygen. And as the bonds go up, it forms this tetrahedral intermediate. And this is going to be favored because if the double bonds come forming again between the C to O, hydroxyl is not a good leaving group. So which means it's going to be favored on this tetrahedral intermediate. And then because we have our solvent water, we can grab one of the H's here in a protonation step, and then we get two uh, two alcohols or a diol, right? So a di alcohol diol, right? And then this can happen also in under acidic conditions, right? So let's say we have this compound here, H3O. Again, this can be any acid. I'm just using H3O. So now in this case, again, remember that we have a delta negative and a delta positive, right? So this is going to be a little bit more tricky. Because my oxygen has lone pairs, I can grab a hydrogen from that acidic, from the acid, right? And then we form this, right? And then if we do a quick formal charge, which is this H right here, if we do a quick formal charge, oxygen has a positive formal charge, right? But there is resonance here. There are double bonds that we can choose. The double bonds here will actually go up to that oxygen, making it a resonance stabilized structure, right? And then the positive didn't just go away. Which element lost? So this carbon had 1, 2, 3, 4 bonds, right? But in this, it only has 3 bonds now. So this carbon is now a positive, right? And because we have a positive now, we can react it with our water that we just had right here. So if we add it with water, it's going to attach to that, and it's going to make this compound, right? And then, oh, I should probably get some space here. Okay, that looks a bit better. Sorry, it's a little bit messy, right? So it looks like that. And then we still have, so this water was from this acid, right? And then now we still have a bit, we still have water, which can then grab this in a deprotonation step over here. And then that leaves us up to this product. And then we also have our catalyst, which is an acid, right? So notice in both of these, we're making the same diol, right? We're making the same diol where we have a carbonyl turn into a 2 alcohols. And in this pH condition of basic, this is a basic conditions, the base attack the carbon, and then we have the base back, so it's a catalyst. But in an acidic conditions, the oxygen up top attacked the hydrogen from the acid, and then we have this resonance structure here, which tells us that this carbon that's attached to that oxygen is actually positively charged, which means something can react to it, and that something is a water molecule that we received right here, right? So it's all actually going to make another diol as well, and we still have our catalyst here. So you're going to be dealing with a lot of these types of reactions, right? So the general idea that I want you to receive from this is that when we have this compound, this oxygen will actually react with any acid. So I'll point it with an H plus, and this carbon can be attacked by a nucleophile, right? So if you see any acid, we know that we're going to be reacting this oxygen. If you see a good base or a good nucleophile, we're going to be reacting it to that carbon, right? Okay. So let's go into acetal formation. So this is an acetal right here. You have a carbon with a ether here. So we have two ethers, a diether. So this is actually called an acetal, right? So let's take a look here. We have these conditions, right? And remember what I said, if you find acidic conditions over here, this oxygen is going to get one of the hydrogens, right? So let's look here. We do have acidic conditions. So this oxygen will take the hydrogen from this acid. I'm not going to show the arrows for that. So it's going to look like this. We still have this OH, and then we have that's all we have. And then we have H2O, which doesn't really matter. And then now, let's do a formal charge. This oxygen over on the left side here is a positive charge, right? But there is resonance where if we pull this up here, this will actually show us that the carbon is a positive charge. Not the carbon and the oxygen have positive charges. Right? And then, do we have a good nucleophile? We do. We have a pretty good nucleophile here in methanol. So this methanol will react like that. And then we form something like OH, right? And then we have this methanol, OH, like that. Boom, right? And then there is a deprotonation step, which is where this water comes in and grabs this hydrogen. We have now this, right? But that doesn't look like our acetal, right? We need another one of these things right here. But look at what happens when this water grabs the hydrogen. It becomes an acid, right? So that means now this oxygen can attack the H again, and then we make it a good leaving group. Oh, I need more space. Let me move this down. So I'll move this up here. Right? So then this oxygen can grab that hydrogen, and then it will become a water, which is a good a good leaving group, because when it leaves, it forms a neutral compound, and it's a weak base. But now we have a carbocation right here. And then usually we make this in excess so that it can react again and again and again. So now we can still react it with a methanol, and then we still have our water here. Because what happens if we react it with water again, it'll just go back to this tetrahedral intermediate, which is, as you know, it's not what we want, and it's not the best thing to do. So we can react it with this hydrogen again, oxygen again. We get this, right? And then this one has an hydrogen here. And then our last deprotonation step is going to give us our acid back as well as our acetal. And then we have H3O. Okay. So that was a little much to comprehend. So let's go back through it together. So we have an aldehyde and we have a methanol under acidic conditions, right? So under acidic conditions, this oxygen from the aldehyde will take the acidic hydrogen from this hydronium compound and form this, right? Because it took this hydrogen, we know that it's a positively charged oxygen, but there is resonance from this carbon double bonded O. And if we show that resonance, we can see that this carbon is positively charged. Because this carbon is positively charged, this methanol can then react to it and form this compound, right? And when we form this compound, we have a positive oxygen, and then we can take the water that we have, which is our solvent, and deprotonate it into this, right? So then we form something like this. But because this water took that hydrogen, it has now become an acid again, right? So this oxygen that had the H in it can take the acidic hydrogen from the hydronium compound and it will form water, which is a good leaving group because this is positive. Now, this can leave, making it a carbocation on this carbon, and then the methanol can then react with it again and do the whole process over again until we form an acetal, right? So it is a lot, but it's a lot of repetition and it's a lot of figuring out where is a nucleophilic center or something of that nature, right? So don't worry, we're gonna keep doing these. We have a bit more to go, and we have 2 more reactions to get through, and then we're done with this chapter. Okay, so this is called an intramolecular acetal formation, and this is gonna look very weird, right? So again, we see that we have alcohols here, and then we have a ketone here, right? Again, same thing. So this ketone is going to react with this acid over here, and it's going to form this, and then this, and then H2O, right? So this is positively charged, but we know that there is resonance, and I'm going to show that by doing this. And then we have this compound now, which is this carbon is positively charged. And then now, do we have a good nucleophile that can come attack it? We do. We have our this di-alcohol species over here. We can choose whichever one. I'm just going to choose this one on the left because it's closer to me. So I'm going to take the double bonds here, the lone pairs, and attach it to there. So now we form this OH, and then this oxygen has an H, and it also has 2 carbons, 1, 2, and it has an alcohol here as well, right? So let's count our carbons. We have 1, 2, 1, 2, we're good, right? And then now this is positively charged. So then this water will come take that, and then it'll go do it again, right? So now we have this OH, right? But we just made an alcohol, a acid now. So if you see where I'm going with this, it's gonna happen again, where now this oxygen is going to take this acidic hydrogen here, right? This one can take it too. It doesn't matter. I just find this one to be a little bit easier because it's on the same carbon. And when it takes that, it becomes a good leaving group. That, right? When it takes that, it becomes a good leaving group, so I can leave. I'm gonna do this, H. And then now, this is where the intramolecular acetal comes in. So what's gonna happen is this oxygen over on this side will actually attack this intramolecularly, right? So if you look, this carbon now will have a bond to another carbon, 2 carbons, and then it's gonna have a bond to an oxygen, which is going to look like this, right? If you look at it, this carbon has the 2 methyl groups on this side, which is what I showed here. It's going to have a bond to the oxygen, which is what I showed here. And then this oxygen is going to be bound to 2 carbons, right? And then this carbon, which is also attached to oxygen. So let's see that in a line notation. This is a little bit harder to see, and it's okay if you don't see it, but do this practice yourself, and then hopefully you are able to see it. So we have this oxygen up here. It has 2 carbons, and we have an oxygen and an H, something like that. And then this is positively charged. And then we still have a water somewhere around here because it's in excess, and then it can come and grab this hydrogen, making a weird looking face like that, right? And then we get back our acid, right? So let's see if we did this correctly, right? So we have 1, 2, 3, 4, 5 carbons. Let's see how many carbons we have here. 1, 2, 3, 4, 5 carbons, which is good. We have 2 oxygens here, 2 oxygens here, and it looks like we are good with this. So this is still called an acetal, and yeah, this is a long reaction, but again, the chemistry is very it's very tedious. It's very repetitive. The steps are repetitive, right? A lot of like deprotonation, as you can see over on this side, and a lot of like reacting it with another acid, leaving group, and then reacting it with a carbocation. So my tip here would be make sure you count your charges, right? You don't want to mislabel a charge here and forget a step. Make sure you count each formal charge and keep track of your formal charges, okay? So our last one is called an imine formation. So an imine is a carbon double bonded to a nitrogen, right? And so we still have the same. We have a ketone, and this is called an amine, and this is under acidic conditions, right? Again, the same steps. Sorry. Okay, let's put that all the way down there. I need as much space as I can, right? This oxygen is gonna come take that hydrogen from that from that hydronium compound. So we're gonna make something like this. Plus RNH2 plus H2O, right? And then if we see again, positive on the oxygen, this bond comes up in resonance. It makes a positive on that carbon. And then now we have a bit weirder step here. This nitrogen with its lone pairs is going to come attack that carbon because it's a okay nucleophile. NH, and then we have R, right? NHR, H2. And then if we look at the formal charges of this nitrogen, it's a positive formal, it's a positive formal charge, right? And because of this, the water can come take it. So I'll show that step. Something like that. NHR, right? Plus H2O, right? And then now, because of this, this water is going to, sorry, this is going to be H3O, right? Because this water just received a hydrogen, right? And now because of this oxygen is going to take the acidic proton, OH, H, and then NHR. Keep in mind this has lone pairs, which will be important later on. And then this leaving group will leave because it's a positive. We have NHR, something like that. Carbocation right here. And then now, this is the important part. We have to figure out that there is resonance here because this nitrogen has lone pairs that we can form a double bond with, right? NHR. So the lone pairs on this nitrogen comes up to form the double bond between the carbon and nitrogen. And then now we have a positively charged nitrogen, which we can deprotonate using our water. So it's going to look like this. Comes up here, and then we make our imine where it's going to look NR. Okay? Yes, that is very, very long, but there is a trick to this. And the trick comes in realizing that what we're actually doing is we're just switching this oxygen for the nitrogen in the R group, right? So let's look at here. This carbon was double bonded to an oxygen here, but now our product, this carbon, is double bonded to a nitrogen and an R group. So if you ever see anything like this, I'm going to do it this way since it's going to be a little bit easier to see. R or H plus an amine like that. If you look at here, we're actually going to be taking away a water molecule, right? This oxygen and this H2. If that happens, we form this compound, RCR, and then double bond NR, right? Can you see how that happens? The water is basically going to be taken out. The O is going to be replaced with the nitrogen, and then this R group, whatever the R group is. So that's just a little shortcut. I'm just showing you this in case you have to understand the mechanism, but it is a fairly long mechanism, and spend some time with it. Like I said, it's going to be repetitive. It's going to be something that you can, if you look at it once or twice, it's going to be there, and I promise you, you're going to understand it. Okay. And then our last one are acetals and as protecting groups, right? Remember, acetals are something like acetals are this type of compound right here, right? It's bonded to a carbon like that. So these are acetals. So what actually happens is if you want to, so let's say you're given this reaction, right? So the reaction states or the problem states, how do you turn this compound into this compound, right? So we first have to look at what's changing. Let's look at our benzene ring. Benzene didn't change here, right? So that's not changing. This ketone stayed the same, but this carboxylic acid got turned into um, a primary alcohol, right? So a carboxylic acid got turned into a primary alcohol. That's called a reduction, right? And then to do this, we have to use LiAlH4, right? But what happens if we use LiAlH4? This ketone actually gets um, reduced as well into a secondary alcohol, right? But if we look at here, this ketone stayed the same. So what we actually have to do is we have to react it with something that will give us an acetal, which is this under acidic conditions, right? So that will actually form this compound. I think it'll look something like this. Something like that, right? And now, because now this is occupied by this group that is not as reactive, then we can fill it with lithium aluminum hydride. And and when that happens, this um, this carboxylic acid gets reduced into a primary alcohol, right? But then we still have this acetal group, right? So what's going to make it turn into a ketone is if we react it with an acid underwater, right? So take time to look and go through this mechanism yourself. This is going to be the most interesting part here. And I just recommend you react it with this oxygen at the top, react it with this acid here, and then do your thing that we just learned, right? So that's it. I hope I didn't go too fast. There's just a lot to cover. But if you need anything, I'll be here. Okay. Good luck.